Okay, here's today's molecule. It's glutamic acid on the left. Um, so we have, well, a couple different potential acidic protons. You've got both of the carboxylic acids, which are different, right? Because the molecule is not symmetrical down the middle. Um, and then, I don't know, the NH2, maybe that could be acidic. Um, I'll go ahead and tell you that that proton in pink is the most acidic, and we'll be able to determine that at the end of today based on some rules. If you treat glutamic acid with sodium hydroxide or sodium carbonate or a bunch of different bases, you get the anion of glutamic acid, which is glutamate, and there's one sodium associated with it, so it's monosodium glutamate or MSG. And of course, this is the stuff that makes food yummy, and does not give you Chinese food syndrome. That is a myth. All right. So, predicting acidity without using pKa values. This is really convenient because the pKa table that I gave you only shows, what, a dozen or so different potential acids. And sure, you can sort of extrapolate and say, okay, if a molecule has like one extra methyl group, it's probably not going to affect the acidity too much. Um, but what about things that aren't similar to things that are on the pKa chart? Well, we can figure that out. And the way we determine how acidic something is by looking at the stability of the conjugate base. So if we have a stable conjugate base, that means the acid that it came from is strong. So if we have something like this, HA is our acid, and A is our conjugate base. If A minus is really stable, happy to be A minus rather than HA, then that means that our equilibrium is going to get pushed in that direction. And then the acidic proton is going to be much more liable to go on to B. Right. And that's what it means for something to be acidic, that it can donate a proton. So we want a stable conjugate base to give us a strong acid. Now we're going to have to look at the structure of, well, really the conjugate base to determine how stable it is. And the way we're going to sort of quantify that is with the acronym REO. And that is four different properties in order of priority that we'll have to analyze. So first is atom. Resonance. Induction, and orbital. So if we're going to do these in order, and if we go ahead and find that just in the first step, the atom that we're looking at is going to make a difference between more stable and less stable conjugate base, then that immediately makes the decision for us, and we don't have to continue on to the next steps. So Let's look at each of these individually. Okay, atom. Okay, we want to see which atom has the negative charge. So obviously this is kind of where our HA and A minus example breaks down. But let's compare these two acids, potential acids. And we want to see which of these two pink protons is more acidic. So the first thing we want to do is, well, I mean, this whole process, we're looking at the conjugate base of these acids. So the first thing we're always going to do is draw the conjugate base. If you can do this in your head, that's fine, but I would recommend drawing it out. So the conjugate base is just the molecule donating that pink proton to something. Doesn't really matter in this case where it goes. And here with the hydrocarbon on the left, make sure you don't add or subtract a carbon in the process. With the alcohol, it's a little more difficult. Yeah, yeah, lone pair on that carbon with a negative charge. And now we just compare the atoms that have the negative charge on them. So this is a carbon versus oxygen. Okay, so now we have to figure out which of these is happier with the negative charge. If your two elements are in the same row, the more electronegative atom wins. So let's do our periodic table here. Okay, so we're comparing carbon and oxygen. And so, right, electronegativity increases as you move to the right on the periodic table. So oxygen is more electronegative. The more electronegative atom is going to be the more stable conjugate base. And the more stable conjugate base is going to have the stronger, or is going to, it will come from the stronger acid. Okay, so that makes it honestly really easy in a lot of molecules to eliminate a bunch of different potential hydrogen atoms from being the most acidic. So if you have a ton of different biomolecules have, for example, just carbon, nitrogen, oxygen, and hydrogen. And so if you want to figure out where the most acidic proton is on one of those molecules, well, immediately carbon and nitrogen and their protons are not in the running at all. So just look for the ones that are on oxygen. Those are going to be the most acidic, at least among carbon, nitrogen, and oxygen. Now, we're going to see a counterexample here in a moment, but generally oxygen is a good place to look for strongly acidic protons. Okay, I talked about the two elements being in the same row, but what if they're not in the same row? So an example of that would be water versus hydrogen sulfide. Again, the two protons are identical on these two molecules. Conjugate base of water is hydroxide. And for hydrogen sulfide, it's SH minus. All right, so our atom bearing the negative charge. Here we're looking at oxygen versus sulfur. So these two are in the same group. They're above and below each other. And so in this case, we're going to look for the larger atom. Sorry, that should go here. Okay, so sulfur is the larger atom. That means SH minus is the more stable conjugate base. And so that means H2S is a stronger acid than H2O. Now, I know here we're talking about comparing the acidity of two different molecules. And like just above, I talked about maybe one of those biomolecules that has multiple different protons on the same molecule. And in this case, it doesn't matter if the two protons that we're comparing are on the same molecule or not. So these examples that I'll give you as we go through these rules are mostly on different. I think they're all on different atoms, so different molecules. And then at the end, we'll do an example where we have one molecule with a bunch of different protons. The comparisons work exactly the same. And then, of course, every molecule is as acidic as its most acidic proton. Again, we'll see that in a moment. Okay. I also didn't talk about like what happens when I don't know, carbon versus phosphorus. So like when we have to look diagonally, we're not going to talk about that in detail. It's complicated and not consistent between the different elements. So we'll just focus on comparing in the same row and in the same column or group. Okay, sorry, REO, atom resonance induction orbital. Okay, so step 2 is to look for resonance. So which conjugate base is more stabilized by resonance? Speaking of resonance, make sure you turn in your homework. Okay, so our two molecules for this one going to be ethanol versus what's this one? Acetic acid, vinegar. So, okay, again, one of them's called an acid, so maybe that one will be more acidic, but let's see if it follows the rules. First thing we need to do is draw the conjugate base. So we'll deprotonate each of our two acids. And just because ethanol isn't called an acid or doesn't have acid in the name doesn't mean that it can't act as an acid. Okay, so there's our conjugate bases. And now, do we have resonance? Now, it may be the case that neither of them have resonance, and then this rule doesn't help, or it may be the case that both of them have resonance structures, and then you got to compare like how many does each one have. Fortunately, in this case, it's very clear very quickly. Can we draw any resonance structures of the conjugate base of ethanol without breaking our two cardinal rules for resonance structures? I don't see anything. The only thing it looks like we might be able to do is move these electrons here, but that would violate the octet rule. So nope. So no resonance structures here, no resonance stabilization of the conjugate base. However, we can draw a resonance structure of the acetate ion. And we can do that by moving those electrons down there, moving these electrons up. I haven't drawn my lone pair on the oxygen. So we can draw that resonance structure of the acetate. And that shows that there is resonance stabilization of that negative charge. There's, right, the negative charge sort of exists in two possible places. Really, it's sort of spread out across the whole molecule. All right, and so this structure is resonance stabilized. And the conjugate base that has more resonance stabilization is going to come. If you can draw a resonance structure, there's resonance stabilization. Yep. So we can't do that for ethoxide, conjugate base of ethanol. So there's no resonance stabilization. There may be inductive stabilization, which is the next step, but we're just talking about resonance. And so the one that has resonance stabilization will be the stronger acid. Now, note that I wasn't drawing resonance structures of the acid itself. That might get you to the right answer. It also might not. So make sure that you draw the conjugate base before you do anything. And so it's just as a general note, right, acetic acid is a very common carboxylic acid, but this basically this, I could just write R here and that wouldn't change the answer. And so this shows you one of the reasons, well, it's really two of the reasons why carboxylic acids are as acidic as they are, because right, the negative charge is always on an oxygen, and oxygen is a fairly electronegative element, beats carbon and nitrogen, certainly. And we always have at least some resonance stabilization of the negative charge. So those are the first, it often wins the first two rules versus other compounds. Okay, Ario, atom, resonance, induction. Okay, three is induction. Now, I will say right, these are in order of importance, one, two, three, four. The first two are far and away more important than three and four. Not that three and four are not used to differentiate. Um, but you will find that in the vast majority of cases, you only need the first two rules to figure out the answer. There's often a difference um, in atom or resonance between two different um, potentially acidic protons. Okay, so we're going to compare for induction acetic acid versus trichloroacetic acid. Okay, same molecule, but the hydrogens on the left have just been replaced with chlorines. Looks crazy, but you can buy this and it's not horribly expensive. Okay, so if we remember from, okay, well, I'm getting ahead of myself. Let's draw the conjugate base. So I mean, technically, with the example on number two, what we should have done first is go back up to the first step because the first one's always most important and look at the atoms, right? Okay, well, they're both oxygen in this case. So rule one is not useful. And then we can sort of do the same thing for number three. We need to go through rules one and two, or example three. We need to go through rules one and two to make sure that those don't differentiate. So REO, atom, the hydrogen is on oxygen in both cases, so the atom doesn't matter. Resonance. Can we draw a resonance stabilized version of these two conjugate bases? Yes, and they're both, this is the same resonance structure, right? We can draw the carboxylic acid resonance structure for both of them, but nothing else. So in this case, there's no difference in resonance stabilization between the two. So now we have to look for inductive stabilization. So remember the induction arrow from reviewing chapter one, this guy, that points toward the more electronegative atom in a polar covalent bond. Okay, and when we have an induction arrow pointing away from our negative charge on the oxygen atom, for example, that means that the electronegative atoms are able to pull some of the electron density away from the negative charge. And in some ways, it's kind of like resonance, but not exactly, because it's essentially spreading the negative charge out over a slightly larger area. So let's see, induction. Okay, so we don't have any very electronegative atoms here. And these are just hydrogens. Hydrogens are not particularly electronegative. Typically, we're going to look for halogens, right? So chlorines, right? There's a carbon in the middle here. And so each of these carbon-chlorine bonds has an induction arrow pointing toward the chlorine. So well, actually, I suppose it wouldn't be a bad idea to draw out the lone pairs on the chlorines, a bunch of them, but right. Halogens love electrons, so they're pulling electron density away from that carbon atom, which in turn is allowing electron density to sort of just, I don't know, kind of just generally be pushed in this direction, right? So that takes some of the negative charge away from the oxygen, spreads it out, and makes it more stable. So that means that this conjugate base is more stable than the regular acetate. And so this one with the chlorine is a stronger acid. And I guess it might not surprise you too much to find that if you just have one chlorine instead of three, it's somewhere in the middle. Two chlorines, a little bit more. Okay, REO, atom, resonance, induction, and finally, orbital. Okay, and the question we want to answer here is which, well, really we're talking about the negative charge here, but negative charge isn't a physical object. So which electrons that contribute to the negative charge are in an orbital that are closer to the nucleus? That's going to be more stabilized. So that, I don't know if that really helps quite as much as maybe this example. So we have an alkene versus an alkyne. And we're going to compare these two protons. And so as usual, we draw the conjugate base. So we remove the proton, give it a lone pair and a negative charge. Is that adequately loud? Check. Wanted to make sure I slammed it a little bit. Okay. All right, so there's our conjugate bases. Oh, they're leaving. Okay, so we're looking for the orbital that those, I think we can see the lone pairs now, the orbital that the lone pairs are in. And for that, we need to look at the conjugation of the carbon atom. The conjugation, the hybridization, they're related, I guess, the hybridization of the carbon atom. So alkene carbons, sp2 hybridized. Alkyne carbons are just sp hybridized. It should really be down here. Yeah, so the lone pair here is an sp2, lone pair here, sp. And so I think we talked about this a little bit at the beginning of the course, but the s orbital, right, is the sphere that's really close to the nucleus. And the p orbital is the hourglass kind of figure 8 shape. So the s orbital is on average closer to the nucleus than the p orbital. So that means that whichever of these two has more s character, it's going to be closest to the nucleus and will be more stable. Okay, so you could think of sp2 as being spp, right? Like in math, an exponent. And so spp versus sp. SP has more S character, less P character. Okay, so this orbital closest to the nucleus. That's the more stable conjugate base. And so the alkyne is the stronger acid. It's not a coincidence that this is the last one because it's really the most kind of nitpicky example. Um, and additionally, this is almost only going to come into play when we're talking about alkynes, right? Comparing alkyne hydrogens to really any other various CH bond. In fact, alkynes are, significantly more acidic than alkenes, but they're still not particularly acidic. You can look on your chart and you should find that the pKa of an alkyne is lower than that of an alkene. Low pKa means stronger acid. Before we do some practice problems, any questions on those 4 rules? Cool. So now, rather than comparing different molecules, we're just going to look for the most acidic proton on one molecule that's got a bunch of hydrogens. Atom resonance induction orbital. So go ahead, take a couple of minutes and tell me which hydrogen you think is the most acidic. There's a bunch of them. 1, 2, 3, 4, 5. Yeah, 6 different types of hydrogen. You don't have to rank them or anything, but uh-oh, I think I drew. Oh no, I drew it wrong. Crap. Um, well, we'll use this one. Ugh. Okay, sorry. What do we think here? Is it any of the hydrogens that are on carbons? No. So it's going to be either this one or this one. Okay, so that's atom. oxygen. Resonance. Are the conjugate bases on either of those positions involved in resonance?
No.
Nope. They look like carboxylic acids. In fact, in the correct in the, example I meant to give, the left one was supposed to be an actual carboxylic acid, but alas. So that doesn't help differentiate between the two. Then induction. So we do have an inductive stabilizing group here, the three chlorines, or fluorines, or bromines, or whatever.
Right.
Well, that means that that conjugate base, where we've just deprotonated the OH on the right, is going to be stabilized by induction. And then there's no induction over on the right-hand side. We don't have any super electronegative atoms. So that makes this the most acidic proton on the molecule. Okay, left to right. But this one has resonance.
Specifically though for the priority list, it's atoms, and then the state it's the atoms, the electronegative. So the S in sulfur is more electronegative than oxygen.
Yep. It's not more electronegative, but it does win. Yeah, I know what you mean though. S is larger than oxygen. So this wins the atom rule. It is still good to note, though, that that one wins resonance. And so if you were comparing this one as well, then that one's going to come in last place because it doesn't have the larger atom, doesn't win the atom rule, and it doesn't have resonance either.
You can't have like so much resonance that it, makes sense.
Not for our purposes. Yeah, it's possible, but these don't really know of any good examples. Okay. Do it correctly. Make sure I'd actually draw this one correctly. All right. This was the this is another pick the most acidic proton. This was on my very first organic chemistry exam, and I got it wrong. Okay, so we're gonna see if we can figure out. Well, I'm going to tell you. I'll let you answer it. Then I'll tell you which one I said, and then we'll talk about why it's wrong. Let me see if I wrote anything else in my answer. Damn, it was 4 points. I lost 4 points. Okay, which one can we eliminate? C, we can eliminate C. Well, technically, the first we should eliminate are all the carbon hydrogens. They look distracting, but only focus on the oxygen in this case. A and B, we can draw, it looks like we can draw resonance structures of those. C, we cannot draw any resonance structures. Okay, so A or B, which one do we think? I heard more B than A, which is good. So I put A, and it's not, it's B. Okay, so let's see. Okay, let me put this down here. So conjugate, um, well, I think C is the easiest to eliminate because it's not next to a double bond. And so there's no resonance structure that we can draw that we can see immediately to draw for C. But A and B, you look at them, you go, oh, there's a double bond in there, there's the carbonyl. Okay, we can draw some resonance, right? I think the reason that I and probably a lot of other people on the exam put A is because it's near the carbonyl. And we know we can draw resonance structures of the carbonyl, right? But what I didn't do is actually draw it.
How do you find a conjugate base?
So here, well, saying conjugate base of A isn't real. It's not technically a real thing. What we're saying is, I'm going to draw the conjugate base of the molecule wherein A is deprotonated. So B is still going to be there with an OH, but A is now going to become an O minus. Okay, and then it's kind of just arbitrary. I'm saying that I just want that at the top to be A, and I'm gonna draw the molecule where just A has been deprotonated, and then the other one, I'm gonna draw the molecule where just B is deprotonated. All right, so this goes away. That becomes OH, and then this. Okay, so really what we're comparing is these two molecules. So now resonance structures for these guys. Okay, for A, let's see. So clearly electrons are going to come down here It's about the only thing we can do. And then from this point, what can we do? We cannot involve the carbonyl, right? Because there's not a pi bond in between here. We can't break this single bond. And so the only thing that we can do at this point is take this pi bond and move it onto that carbon atom. Let's see, so that becomes this OH here, and then lone pair right there, okay? So that's a resonance structure for the conjugate base of A.
Can you write that as a double bond instead of a nuclear?
Double bond where? Between the carbon and the oxygen?
Yeah, on the third one. Like, when you move that double bond.
Ye-
So, yeah,
Yes.
the. Oh, is that a nuclear?
What do you think? So no, because, right, this oxygen here already has an octet. And so we can't move that lone pair toward the oxygen. That will break the octet rule for the oxygen. Admittedly, this is not a very good resonance structure, right? The top one is still a better resonance structure because the negative charge is on the more electronegative atom. Okay. Now, can we draw a resonance structure of B? So we're going to do kind of the same thing where we bring electrons from the oxygen down, right? We're pretending that these are two completely different molecules. Now what we can do is move this pi bond over and move the pi bond up onto this oxygen. We can do that without violating the octet rule. This was a mean problem. And this was on the first exam too. Okay. It all comes back to resonance structures. So when we're comparing the quality of the resonance structures, which would like, for example, trying to pick which contributor is the major contributor, right? Between these two, the one where the negative charge is on the oxygen is a clear winner. In this case, these are actually identical. You just flip the thing around, excluding this OH, rotate. But we have a negative charge in oxygen in both cases. And so that means that this, the conjugate base of B, has better resonance stabilization than A. So that means that the proton here is the most acidic. So what does that look like in an actual chemical reaction? That would mean that if we took, sorry, I'll go back to that in a second. Uh, If we took this molecule and added just one equivalent of sodium hydroxide, so 1 mole of the starting material and 1 mole of sodium hydroxide, which position will be deprotonated? Well, it's going to be the most acidic proton. So we're going to get the conjugate base where that proton is removed, sodium plus, and then water as a side product. I will not put that on the exam. But hopefully here you can see how the resonance structures and the acidity kind of go hand in hand. Questions on Ario? Clear as mud. Okay, we'll stop here for today. I think that's a good stopping point.